Welcome to this video. So in today's lesson, we are going to go over some questions on determinants. This is tutorial sheet 3 of linear algebra. Okay. So in this video specifically, I'm going to answer the questions on question 1, which are just simply true or false questions. Okay, so we have to state if a given statement is true or it's false. And then when we choose either of those answers, we have to prove, okay, or give a justification whether what we've said is truly true or it's false. Okay, so we start with A there. Okay, so the general question they're saying for each of the following questions, state with justification whether the given statement is true or false. Okay, so the first one they're saying if the determinant of the matrix is 0, then the matrix is invertible. Okay, so what does it mean to be invertible? Okay, to be invertible, it means the matrix has an inverse. Okay, it means the matrix has an inverse. So if the determinant of this matrix, let's say matrix A, is 0, okay, will this matrix have an inverse? Okay, that's what they are asking here. So the answer is no. Or we are going to say that statement is false. So now we have to give a justification where we are saying it's false. Okay, so in the formula for finding the inverse, we say A inverse is actually equals to 1 divided by, okay, the determinant of A, and then we multiply by the adjoint of A. Okay, so now if this determinant here is 0, we are going to have a situation where we are going to have 1 over 0. And we know that 1 over 0 is what? Undefined. Okay, so since the determinant is 0, it means this matrix A won't have an inverse there. Okay, so it won't be invertible. It will have no inverse. Okay, or it will be non-invertible. So the first one we are going to say false. And then this is the reason here that you give. All right, let's look at B. So B, they're saying if two columns of a matrix are negative scalar multiples of each other, then its determinant is 0. Okay, so there you're just using the properties of determinants. Okay, so if you have a matrix, let's say matrix A, which is in the form, okay, I'll just pick any numbers here. So maybe 3, 1, 2, 4, 5, 0, okay, and then 1, let's say 2, 2, okay, and then when we apply the row echelon form on this matrix, okay, maybe we find that the last two columns here become so I'm not showing the whole process, but maybe the last two columns become something like this. So maybe I have there I now have 1, okay, 2, 4, and then the last two columns, okay, or one of these out of these 3 columns, okay, 2 of them are negative scalar multiples of each other. Okay, what will happen? So it means here I can have maybe okay, I will just write 1, okay, to simplify things. And then here, okay, let me put this as -2, even this one as -2. And then here you can put anything. Okay, so we see that these 2 columns here are negative scalar multiples of each other. So what happens, okay, when we reduce it into the reduced form, okay, the row echelon form, it means that these columns, okay, they are going to end up being zeros. Okay, because this here, when we apply column operations, okay, we can make this column here to be 0. So if one of the columns is 0, okay, or one of the rows is 0, then it means the determinant is 0. Or you can look at it from this perspective, okay? Since here they have said 2 columns are negative scalar multiples of each other. So what does it mean to be a scalar multiple of each other? Okay, it means those 2 columns are linearly dependent. Okay, so it means one of the columns depends on the other one. Okay, so if one of the columns depends on the other one, okay, then what will happen? It means one of those columns here will collapse to 0, 0, 0, 0. Okay, so if we have one row which has all zeros, okay, or one column which has all zeros, then it means the determinant of that matrix will just simply be 0. Okay, so here we're going to say this statement on B is actually true. So why? Because here they've said the columns are multiples of each other. So it doesn't matter if they're positive scalar multiples of each other or they are negative scalar multiples of each other. As long as they're scalar multiples of each other, it means one of those columns is going to collapse to 0, 0, 0, 0. And then if we have one column with all zeros, then we're going to say the determinant of that matrix is simply what? 0. Okay, so that's the explanation on B. And then let's try to look at C. So C is very simple because it's one of the properties of determinants that was given in the notes. Okay, so they're saying for any two n by n matrices A and B, the determinant, okay, of A plus B is actually equals to the determinant of A plus the determinant of B. Okay, so is this statement true? Okay, so in general, we're going to say this statement is not true. Okay, so we can say this statement does not equal the right-hand side in general. Okay, and then we can give a counter example. So let's say I have matrix A, which is 1, 0, 0, 0, and then I have matrix B, okay, which is 0, 0, 0, 1, okay, and then matrix A plus B, we are simply going to add these two matrices. So we're going to have 1, 0, 0, 1. Okay, so now let's find the determinant of A. So determinant of A will simply be 0. Determinant of B will simply be 0 as well. And then the determinant of A plus B will be 1 multiplied by 1, 1 minus 0 multiplied by 0, which is 0. So this will give me 1. Okay, so you see that if I add the individual determinants, okay, I add determinant of A plus determinant of 0, it's not equaling the determinant of A plus B, which we found here, it was what? 1. Okay, so that's the justification that you give there. So in general, this here is not true. So we're going to say that statement there is false. Okay, we move to D. So on D, they're saying the determinant of the inverse of A, okay, determinant of inverse of A is always equal to minus the determinant of A. Okay, so this one here is false. This is not true. Okay, so the correct formula for the determinant of A inverse is actually 1 over the determinant of A. So the determinant of the inverse, okay, is simply the reciprocal of the original what? Determinant of the matrix A. Okay, so sometimes they will give you this one here to prove. They will say, prove this. Okay, so how do you prove that? Okay, how do you prove that? So you're going to say, okay, let A be a matrix that is invertible. Okay, so if A is a matrix that is invertible, it means the inverse of A exists. Okay, and we know that if I multiply A with its inverse, what am I going to get? I'm going to get the identity. Okay, and then both on both of these sides, I'm going to apply the determinant like that. Even this side, I apply the determinant like that. Okay, so here, by one of the properties of the determinants, we can separate these two. So it will be the determinant, okay, of A multiplied by the determinant of A inverse is equals to the determinant of what? I. All right, and then from here, we're going to say this. Okay, so I can erase this. From here, we are going to say determinant of A inverse is actually equals to the determinant of the identity divided by the determinant of what? A. So the determinant of the identity there is always 1. Okay, as long as you have an identity matrix, its determinant will always be 1. So this one here will just be 1 over the determinant of what? A. Okay, and this is the correct definition of the determinant of the inverse matrix. It should be like this and not the way it has been given here, where they're saying the determinant of A inverse is actually equals to minus the determinant of what? A. So this statement here we're going to say it's false. The correct one is this. Okay, so on D here, we're going to say what? False. Okay, and then let's look at E. Okay, so on E, they're saying if a square matrix A has a row of zeros, then the determinant is zero. That one is straightforward. Okay, that one is true. Okay, so if it has a row of zeros, so for example, if A is equals to 2, 5, 0, 0. Okay, so this is the row of zeros there. So whenever one row is completely filled with zeros, or one column is completely filled with zeros, then that the determinant of that matrix just becomes 0. Okay, so if we try to find it here to be 2 multiplied by 0, 0, 0 multiplied by 5 minus 0. So the determinant there is what? 0. Okay, so always, if you have the whole row being comprised of zeros, okay, we are going to say the determinant of that matrix is always what? 0. So that is true. Okay, so this one is very simple. And then we look at F. So F, they're saying the determinant of A transpose is actually equals to minus the determinant of A. Okay, so is this statement true or false? This statement is false, because by definition, you can check your notes, the determinant of A transpose is actually equals to the determinant of what? A, and not the negative. Okay, so this negative here makes the whole thing wrong. So this one is wrong. So we're going to say it's false. Okay, because the correct one is given like that. So if you want, you can come up with a matrix. Let's say 2, 4, 7, 9. Okay, then let's find the transpose of that matrix. It will be 2, 4, and then 7, 9. Okay, so you see that the entries in the main diagonal here, they do not change. It's 2, 2, and 9. So when we multiply it, we get 18 minus for both. And then in the minor diagonal, it's just these guys that have switched position, but multiplication is commutative. So 7 multiplied by 4, okay, it's the same as 4 multiplied by 7, which will give me what? To give me 28. So this will be minus 28. The determinant will still be 10 for both A transpose and A. So this one here is correct. Okay, so what we've been told here is actually a lie. So we're going to say this is false. It's not true. Okay, let's look at G. So G, it's a very interesting question, and they like bringing it. Okay, Dr. Mbai likes bringing this question. So here they're saying the determinant of A is equals to 5. Okay, then the determinant of 3A is actually equals to 15 for a 3 by 3 matrix A. Okay, so is this true? Okay, so most of you, what you're going to do here, you're going to say, okay, the constant goes out, and then I have the determinant of A. Okay, so determinant of A is 5, and then this is 15, and then hence proved this statement is true. No, okay, that is not correct. So the correct way of expressing the determinant, okay, where you're multiplying the matrix with a scalar, okay, like this one, this 3 here is a scalar or a constant. Okay, so if I have determinant of a constant, let's say K, multiplying the matrix A, okay, this here is the same as, okay, that there is the same as N, not N, okay, it's the same as K to the power N, and then determinant of the determinant of A. Okay, so this power N here, okay, this power N here represents the order of the matrix. Order of matrix. Okay, to present the order of the matrix. So here we've been told that it's a 3 by 3. So it means my N will just be 3. So now I can find it using this formula. So determinant of 3A will be equals to 3 to the power 3, because the N is 3. The K in this case is 3. And then determinant of A. Okay, so determinant of A, we're given it's what? We can just put it directly here. We're given it's 5. So here we have 27 multiplied by 5, which will give me about 135. So we see that the 135 here is not equal to the what? To the 15. Okay, so we're going to say this statement here on G is actually what? False. This is false. All right, let's look at H. Okay, so on H, they're saying if A is a diagonal matrix. Okay, so a diagonal matrix is a matrix that has all zeros on the entries that are off the main diagonal. So if, for example, A is a diagonal matrix, okay, it means I have an entry there, an entry there. Let me say B here, and an entry there, okay? And then the rest of the places here, we're going to have 0, 0, 0, 0, 0, 0. Okay, so all the entries of this main diagonal here should be 0. And when we're going to call that matrix as the diagonal what? Matrix. Okay, so there are some special rules when you're finding the power of a diagonal matrix and also the inverse of a diagonal matrix. So if, for example, I'm finding A to the power k, okay, A to the power k of a diagonal matrix is the same as I write A to the power k, B to the power k, C to the power k, and then here I put what? I put zeros like that. Okay, and then when I'm finding the inverse of this A, it's the same as, okay, 1 over A, 1 over B, 1 over C, and then here I just put what? I just put zeros. Okay, so these are the special rules that we are going to be applying when we are talking about diagonal matrices. Okay, so now going back to our question, they're saying if A is a diagonal matrix, then the determinant of A squared is the same as the determinant of A, and then we square it. Okay, so let's find A. Okay, so let's say A, because this statement here is actually true, but let's prove it that it's true. So let's say A, okay, is a diagonal matrix where we have I. Okay, let me not use I. Let me use X. So I have X and then Y. Okay, so this is the diagonal matrix that I have. Okay, so let's find A squared. So A squared, because this is a diagonal matrix, we're just going to square this part. So it will be X squared 0, 0, Y squared. As simple as that. Okay, so now let's try to find the determinant of this, and then we see if it's equal to the determinant of this, and then we square it. Okay, so the determinant of X, the determinant of A squared is equals to X squared multiplied by Y squared, and then minus 0. So it's just the X squared Y squared. Okay, so now let's find the determinant of A, and then see if it will be equal to that one if you square it. So determinant of A will be equals to xy. Okay, and then now determinant of this same A that we have, and then we square it, we're going to have what? Xy squared, which will be x squared y squared. So we see that the answer that we get from here, okay, is actually the answer that we have there. So what does that mean? Okay, it means that this statement here that they gave us is actually what? True. So this statement is true. Okay, so next we look at I. Okay, next we look at I. So I, they're saying if A and B are similar matrices, then determinant of A and determinant of B are the same. Okay, so here the answer is that yes, this is a true statement. Okay, so whenever you have two similar matrices, okay, then the condition B is equals to P inverse A multiplied by P should be achieved. So this is the definition of what similar matrices are. If A, okay, and B are similar matrices, then they must satisfy this condition here. So the good thing about similar matrices is that they have three things in common. Okay, one, they have the same determinants. Okay, they have the same determinants. Two, they have the same trace. And then three, they have the same, later on you learn about eigenvalues. Okay, So they have the same determinant, same trace, and same eigenvalues. So the statement there is actually true. So whenever you have A and B being similar, then their determinant should be what? Should be equal. Right, and then let's look at the last one. Okay, so even this last question here, it likes bringing it. Okay, so make sure you know how to solve it. Okay, so on the last question there, they're saying there exists a non-identity orthogonal matrix Q such that the determinant of that matrix is -1. Okay, so this one here, non-identity, they just mean that this orthogonal matrix is not the identity matrix. Okay, because we know that the identity matrix is always orthogonal. Okay, so when they say non-identity matrix, it means they are referring to any other matrix, but that matrix should be what? Orthogonal. Okay, so we know by definition, okay, that if matrix Q is orthogonal, okay, if matrix Q is orthogonal, then it must satisfy the property that its transpose is actually equals to its inverse. Okay, so we also know that if I multiply Q with its inverse, what I'm going to get is the identity. Okay, but now where there's this inverse here, I'm going to replace with the transpose because the transpose is equal to the inverse. So I can replace there. So I have Q and then Q transpose. Okay, so this is what I have. So I can write it like this: Q and then Q transpose is equals to the identity. Okay, and then what do I do from here? I'm going to introduce the determinant on both sides. So we'll say determinant of this, and then even there I'll put the determinant of I. Okay, so this one, by the definition of the properties of determinants, we can separate it into determinant of Q multiplied by the determinant of Q transpose is equals to the determinant of the identity matrix. Okay, but from those same properties of the determinants, okay, we know that the determinant of a certain matrix, maybe A, is the same as the determinant of its transpose. I think we proved this one. Let me go back. Didn't we prove something like this? Yeah, here where we said this statement that they gave us here was wrong because the correct one was the determinant of the transpose is equal to its the determinant of the matrix itself, right? Okay, so here we are saying the determinant of A is the same as the determinant of what? A transpose. So what I see here is Q and Q transpose. So it means this one here, okay, the determinant of Q transpose is the same as the determinant of what? Q. Okay, so here I'm going to replace this with the determinant of what? Q. Okay, so let's erase some things on top here. So what we're going to have now is a determinant of Q multiplied by this one. I'll replace it with the determinant of Q as well. And then is equals to, we said the determinant of this one, the determinant of the identity is always 1. Okay, so on my left-hand side, I have the determinant of Q multiplied by the determinant of Q. So that is the same as the determinant of Q to the power 2 is equals to 1. So this will be the determinant of Q is equals to, okay, plus or minus the square root of 1. So you square root both sides. And since we are introducing the square root here, we put plus or minus. So it means here our determinant of Q being equal to plus or minus what? 1. Okay, so from this statement, I can get that my determinant of Q is equals to 1, or my determinant of Q is equals to what? -1. So that's always the case. Whenever you have an orthogonal matrix, okay, then the determinant of that matrix will always be 1 or -1. Okay, so in our question, they said there exists a non-identity orthogonal matrix Q such that the determinant of Q is -1. So this statement is true because we've shown here that it's a possibility here. Okay, so there are two possible determinants. It can be 1 or -1. And then here they gave us a -1, which is true there. Okay, so we are done with questions on our question 1. Okay, so I also solve all I also solved all these questions, okay, but they're in written form. So if you'd like to access them, you can simply register on our website, and then you'll be able to go there, and then you'll be able to view all these solutions to all these questions here, as well as tutorial sheet 2, as well as the tutorial sheet 1. Okay, and I also have sample quizzes, sample tests that I've uploaded there with their solutions, so you can easily go through. Okay. Right. So when we come to the website now, this is our website. Okay. So you scroll down where you can see linear algebra here somewhere there. So when you open linear algebra there, okay, and then you go to the tutorial sheets, you go to the written solutions, okay, you're going to find the solution. So you can go in 2025 there. Okay, so you're going to find all the solutions, okay, to all the tutorial sheets that you are going to have. So 1, 2, 3 so far. So the solutions to this tutorial sheet that I'm from solving, you're going to find them here. Okay, so you can access them from here. And then now we also have some materials for financial mathematics. So when you go in the financial mathematics folder, okay, you go to the lessons and tutorials here, you're going to find a lot of videos, okay, that we've uploaded. So the way we have approached this is that we teach a certain concept, okay, and then we also solve example problems. So you can see lesson 1, this L1 means lesson 1. So lesson 1 was on compound interest, and then you have the examples on compound interest. Okay, so I'll need to put this in order because after lesson 1, you need to go to lesson 2. But you can just go a bit down there. You're going to find lesson 2, which is on basic cash flows. Okay, so you can watch this one and then you watch the example there. Okay, after that, you go to lesson 3, just like that. Okay, and at the end of each unit, there's this lesson here where we titled it as the review. So we are reviewing all the concepts that we learned, okay, in a certain unit. Okay, so the first unit has lesson 1 all the way up to 10. The second one has lesson 11 all the way up to 19. Okay, the other unit has lesson 20 all the way to 24, and then the other one has 25 all the way to 30, and then the last unit has the lessons 34 all the way to 35. So you can access all these videos here, and then you can learn easily. Okay, so that's that, and then you can also go to the folder for the tutorial sheets here. You can find some solutions. Okay, so you can go there. You are going to find some solutions. I think there are past intakes, and then there's also your intake. Okay, so for your intake, you can see there's 2025 there, something like that. And then Dr. Msonda doesn't usually change the assignments and the tutorial sheet. Okay, so for your assignment 2, you can check the solutions there, assignment 3 there, okay, just like that. And then also the tutorial sheet have some solutions, plus also the quizzes also have some solutions that you can check. All right, so that's financial math. Okay, you can also register for analytical geometry. There's probability. What other course do you take? Maybe real analysis. Okay, you can register and access that. Okay, otherwise, um, thank you so much for watching this video and see you next time.